Excuse me, Carolyn, can you unmute the microphone? Thank you.
All right, sorry about that. Okay, so you just missed a couple of introductions. So thanks, Andy. I could tell that to you for reminding me that it's muted. Continual challenges of the world of Zoom. But anyway, thanks for joining us today. So what we're going to do mostly today is give the graduate students and postdocs a chance to talk about their research. And we have a wide variety of research going on around the center. We have over 30 graduate students whose thesis or dissertation is focused on some aspect of additive manufacturing. You're going to see a lot of them speaking today. So let me just see here. Let me get this thing going. Advance the slides. Just want to give those of you who may be new to us a little bit of an introduction to our Center for Additive Manufacturing and Design Innovation. So in terms of expertise, we have 10 faculty members with over 100 years of combined research experience. Even our operations engineer has more than 6 years of experience and a PhD. And like I mentioned, over 30 graduate students who are focused on doing additive manufacturing related research. And here you can see some of our faculty members. Several of them are here today, and others I think are going to join us as the afternoon wears on. And so we have quite a bit of experience in both materials, design, and processes. So we really go all the way around that trifecta, which I think is really important for additive manufacturing. Other highlights, we have resources. We already have about 3,000 square feet of space in the ground floor of ETC, which is kind of prime real estate. In an engineering building is the ground floor where we can get all of our big equipment in and out. We're right next to our newly renovated machine shop as well. And so we have, you'll see if you're familiar with ETC, if you come in from the back, the loading dock there on the right and walk down that hallway, everything on the left is machine shop and everything on the right either is or will soon be part of our additive manufacturing center. So we have a metals lab. We also have metrology, some metrology nearby. And a liquid polymer lab and also a polymer powder bed fusion lab. And we have these in separate rooms so we can keep cross-contamination down. And then that white room that's right in between the polymer and the metal, that should come over to the center here soon. And so it'll be a really good spot for us to have research test beds and things located as well. And this is just our commercial equipment. We also have quite a few research test beds that are scattered throughout ETC as well as on the Pickle Research Campus and also in the chemistry building. And that's not even included in this count of square feet or in equipment. But here's a view as of a few weeks ago of our metals lab. It's already looks different than it does here. So here you'll see this is our metals machine, our EOS M280, but we also have a Renishaw AM250, courtesy of a really generous donation from Cumberland Additive. And we also have a large size CMM off to the right that you don't see here, but it arrived in the last few weeks since this picture was taken. Commercial capabilities, I think I mentioned this, and all of this has been built up since December. So it's been a very rapid build up. Jared's done a wonderful job of getting this equipment in and getting it set up and getting it all operational. So I mentioned we have an M280 direct metal laser sintering machine. We also now have a Renishaw AM250 direct metal sintering machine, and that should come up and running here in the next month or so. We also have an SLA 5000, so sort of a workhorse of stereolithography. We have a digital anatomy printer from Stratasys, a J750, where we can build biocompatible or bio mimicry types of things. So we can build, for example, heart models that have the same mechanical stiffness as the tissue would from an actual heart. We have powder bed fusion. We have our 3D Systems HiQ machine, which we've had for a number of years. And then we also have a coordinate measuring machine, mechanical property testing. We have a big MTS 300 kilonewton load frame that's coming in here in the next couple of weeks. And then not accounted on here, we also have a couple of large commercial robotic arms, six-axis robotic arms that with quite a bit of payload capability. I think mine is like 80 kilograms, and then Mayron has another one that has even bigger load capability than that. And those are out at our Pickle Research Campus, and you're not seeing those here in these pictures. Other highlights, location, we are really right in the middle of a Central Texas additive manufacturing ecosystem. And these are just a few of the companies that we've interacted with that have offices nearby within a half an hour of driving distance. Plus there are other companies a little further north towards Belton and Temple, where Stratasys Direct has some work, and ALM is still located up there as well. And I think there's still some others that I need, like your company, Juan, I need to add yours to this list as well. So now that we're aware that you're over on Bee Caves, it is on there. M Aerospace RTC. Okay, we got it. Okay, Jared's a step ahead of me on this, always. And then, of course, transformational research, which is kind of why we're here today, our research test beds and things that we can't do with commercial machines right now, but all of the students and postdocs that are with us are making it possible with all the cool research that they're doing. So I'm going to stop talking here in just a second and turn it over to them to talk about all their research test beds and the research progress that we've made. But first, just some opportunities for engagement. We'll come back to this at the end of the day. We do have an industrial affiliates program that we're launching, and that's an opportunity to engage with us on an annual basis and participate in more of these research symposia and also seed some projects with the center. Collaborative research proposals, student internships and projects, and we're also starting to think about educational and curriculum opportunities as well for graduate students and for non-UT personnel. So we'll talk about those at the end of the day, but I just kind of want to seed those in your brain and get you started. So here's our schedule for today. We're scheduled to start lightning talks at 1:15. We're about a minute or two late, so we're almost right on schedule. And that's going to go for about an hour and a half. We have 10 talks, each person talking for about 7 minutes. I think we've asked them to do with a couple minutes of Q&A. So we won't have a lot of time for Q&A here, but we'll have lots of time afterwards. So we have from 2:45 to 4, we have a poster session where we have over 20 posters, I think, set up. Jared will be giving tours of our center. So if you'd like to go check out our commercial equipment, you can do that. We have refreshments, and then you'll also have the opportunity to ask questions of some of our lightning speakers, since we're going to go through those so fast. And then finally at 5 o'clock, we'll have a happy hour over at Posse. And so first round of drinks is on me, or sodas, or whatever you prefer. If you have time, stick around for that at the end of the afternoon. So with that, I'm going to turn it over to Jared's going to get started, and we're going to do our lightning talks. I think Nathan Heathman is our first.
That's right. Thank you for the introduction. Go ahead and bring that up for us. Get your presentation loaded. Okay. Let me share this Zoom window first. All right, can everybody online see the presentation right there? Is the presentation live online? Can everybody see that?
Yep.
Okay, great. All right, so I'll turn it over to Nathan Heathman.
Alrighty, can y'all hear me at all? Good. Okay. All right. Hello, everybody. My name is Nathaniel Heathman. I am with the Tehrani Group. Today, I'm going to give you a brief overview of our research topics, which you can find out more info later by visiting our posters. All right. So the first area of research here is we have essentially figured out how to 3D.
No. Mike, let's turn it around so it points upwards. So everybody.
Sorry, everybody. Better? Okay. All right. So our first area we're going to talk about is we've essentially figured out how to 3D print graphite. So you can see here on the presentation that we mix graphite with cellulose in a water solution, essentially turn it into a paste, which then we can 3D print through direct write. This material is sustainable, doesn't require any energy input. And then after printing, we can either post-process to keep the material around longer, or we can just dissolve it in water and then recycle it. Next area of research is DMLS of pure copper. So this is important because copper is good for high-end electrical components, also heat exchangers. Via DMLS, we can make more complex components. However, the material properties aren't quite as good as the bulk materials. So through this research, we're using one of the printers in the AM Center that Jared provided to basically print test coupons, test their mechanical properties, try to find out more about what's going on in the process that makes these parts weaker. Next area of research here is that through continuous fiber filaments that have been developed in previous years, you can print FFF parts with much higher strengths. One of the applications for this is actually topology optimization. So what we developed is stiffness-based design for a specific loading situation that you can see in this L shape. Run the part through an algorithm to get the topology optimized part, after which we run it through another algorithm to get it actually printable. So this develops the fiber paths with the proper radius in one single path per layer, no loops or anything like that. After that, we print the part in an in-house designed 3D printer. And then we can test it in the tensile machine and use DIC to take a look at its stiffness through testing. This form of research involves high performance thermoplastics polymers, the PEC family. So this is PEC, PEEK, and then PEC again. So what we're doing in this research is basically comparing parts that are printed via SLS, which we know are going to be better, more isotropic, versus FFF parts, which we know are very anisotropic. We've run these parts through some post-processing methods and then compared material strengths between the two to kind of increase the FFF parts and then enable people to use FFF instead of SLS. This next form of research, we know that a lot of the weakness in FFF parts is due to the voids and the thermal history of the part. So this research, we use Digimat AM to predict the thermal history and the void concentrations, and then find ways to improve those, and then we validate through 3D printing and mechanical property testing. This form of research is a collaboration with Dr. C. Prasad's group. We talked a little bit about it. It's the REAM 6-axis robot manufacturing out at the Pickle Research Campus. So this process essentially uses a specialized epoxy material combined with carbon fiber and fumed silica. They have a specialized printing head, which they can deposit this material. The importance of this is that, once it's deposited, it's cured. There's no post-processing necessarily needed. It's also more sustainable because there's no heat input during the printing process. The exothermic reaction just takes care of the curing during printing, and then the part you pull off the print bed is ready to use. The final thing I'm going to talk about today is that our AFP, or automated fiber placement of thermoplastic composites via robotic. So this consists of a KUKA robot with a single toe AFP tool head. We combine this with a 600-watt diode laser system to basically melt the thermoplastic tapes up to melting temperature during deposition. The goals for this are, I'm sure a lot of y'all know that AFP is widely used already for thermosetting materials. Boeing, Electro Impact already used these successfully making aerospace structures. The thermoplastics are the next up and coming. The advantage is that if you process this in situ, there's no need for any post-processing in autoclave. So what we're working on is increasing the understanding of the process itself by doing some mechanical property testing on DOEs. Then we're also going to work on process inspection via high-speed camera, laser system, thermal imaging to look for defects during the layup. And then we also have a bonding model we're working on validating, because that's a big problem in industry currently, is nobody has a good model for this process. All righty. Thanks everybody for listening. If you have questions, please visit the posters. If anybody has immediate short questions, I'm going to open the floor.
All right, thank you very much, Nathaniel, for a great overview of the incredible research that's going on at Dr. Tehrani's group. So our next presenter will be Kevin Zhao. So if he can come on up while I load up his presentation, and we'll keep the lightning talks going. I know this feels like a sprint, but we have a lot of research that we're trying to share. So we've got a lot of stuff going on here at the AM Center. All right, I forgot to share the screen and Zoom again, so I'll do that. All right, and I'll turn it over to Kevin. So you can clip that onto your shirt. Just stick this in your pocket.
All right, can you all hear me? Sweet, sounds good. So, hello everybody, I'm Kevin. I'm a part of the PAID group, and I'm here to give my talk today about shifting the spectrum on digital light processing 3D printing. Let's start. So the way that digital light processing works is that pattern light is shined from an LED projector, and then it is projected into like this mirror device that is then shined up into this liquid resin vat. That pattern light will then generate solid pattern polymer layers that are then stacked onto each other to create the final print. Compared to your traditional extrusion-based methods, digital light processing makes it easier to print out more complex objects owing to the finely patterned light and the fact that their starting material is a liquid resin instead of solid filament. However, the issue is that a lot of DLP methods today utilize UV light to do their printing. While UV light is pretty rapid to cure, it's also rather energetic, and that can degrade the quality of your prints, along with the fact that it also prevents the use of biological applications. Visible light, however, does get you a lot of these advantages, such as biocompatibility, and also this functional root tolerance, and also larger penetration depth and reduced scattering, but it's also rather slow to cure, and the resolution of the prints generated is also rather low. Therefore, our research mainly focused on identifying new PhotoRedox catalysts that would enable fast and high-resolution 3D printing in the visible spectrum, as seen here with these 4 candidates. You can see on the far left, this vapor right here photopolymerizes really fast under 405 nanometer violet light, while on the other side of the spectrum, this zinc TPP right there will initiate really fast photopolymerization under 617 nanometer red light. So we have some pretty nice variation across the visible spectrum, as we can see above. However, and also these PhotoRedox catalysts are very good and can be used in a variety of different resins. For one, if you wanted to say print out a really hard and stiff object, you could stick your PhotoRedox catalyst system into this system on the far left made out of DMA and TMPTA and get a hard, stiff print. If you wanted something that was softer and stretchier, you could then stick your PhotoRedox catalyst into a softer resin made up of these monomers to the right, this HIA and this TEGA. That gets you something that allows you to print out something that's a lot softer and stretchier. However, it's not quite as simple as just simply putting in your PhotoRedox catalyst into your monoresins and letting them go. Here is an example of a resolution print that we actually use to analyze quantifier resolutions. We can see it's pretty rectangular on the outside, and inside the middle we have 12 squares with a number on there. That number corresponds to the amount of seconds that red layer is exposed to visible light. However, though, when we actually print this out though with our resin, we see that it's actually rather undefined and blobby on the edge. You can see it's pretty rectangular. Resolution is really, really, really low. And also, if we see circled in blue, we have some notching in the middle of the print that is known as cure through. The reason why this phenomenon is observed is simply because of light diffraction. So essentially that pattern light will hit that target area and create that desired polymer layer, but then some of those photons will scatter and diffract through the resin and trigger undesired polymerization elsewhere in the system. And that is the reason why we get this like lower resolution and this blobbiness that you saw in the previous photo. The solution that we found was to use a type of compound known as an opaquing agent. These opaquing agents absorb certain wavelengths of light and prevent it from diffracting through, as you can see in the figure to the right. And that essentially keeps that pattern light into that region and allows for more sharper resolutions. We can see right here that once you dope that resin with the opaquing agent and print it out, you can see that it's a lot more defined, a lot more rectangular and a lot more detailed. Looks a lot closer to the actual print file, so we have some really nice resolution increases there. The downside, though, is that you can see that that 1 second skirt on the far left no longer actually appears. And that's just simply because of the fact that like the opaquing agents do absorb some light, and that slows down your polymerization. Therefore, one of my jobs in this project was to basically find that sweet spot that balanced out accuracy of resolution with high polymerization speed. Too much opaquing agent and you get nothing at all. But if you don't have enough opaquing agent, then basically their print looks really inaccurate, and then there's really no point to doing it. Additionally, there is another problem too that just simply comes from the oxygen we breathe in the air around us. What happens is that oxygen can come in, it can basically interfere and bind with these catalysts, as you can see right here. And the end result of that is that essentially interferes with your polymerization reactions, and the prints don't go to completion. As you can see right here, where we're getting the 1 and 2 seconds don't show up, and even at like 5 seconds, we're struggling to get a lot of detail on this resolution print. Thus, the solution that we found was to use inert gas flow. So essentially, our printing chamber here is hooked up to a tank of some sort of inert gas, namely nitrogen or argon. And then as you're printing through, you basically flush the atmosphere with a flow of inert gas. What that does is that the inert gas will displace the oxygen from the atmosphere and in the resin and prevent it from interfering with their catalytic cycle. And that allows your polymerizations to go to completion and for prints to look a lot more high in resolution. We can see right here, we take that same resin with the zinc TPP inside. And when we actually print it out without the oxygen, with the oxygen removed from degassing, we can see a lot more detail. Even at like 2 seconds, we're getting a lot of the tiny pixels showing up, which shows a marked increase in resolution, which is what we exactly wanted to see. We can also make some additional, more complex prints with this, such as this truss right here, where we can see that our digital rendering to the left and also the printed results to the right look a lot pretty close to each other. That's very good. We want this high resolution, and that's going to be good for future prints. However, it's not going to be that simple because of the fact that, again, this requires inert gas. And I'm presuming that most of you don't have, say, a tank of argon lying around somewhere in your garage. So to make this more accessible to the average consumer, we dope our resins with a type of a compound known as a thiol. This thiol, as you can see to the left right here, this PETMP, that scavenges oxygen from the atmosphere and inside the resin. And by doing so, that'll prevent it from interfering with the catalytic cycle and allow your photopolymerizations to go to completion and a lot faster. As you can see in the figure to the right, where we can see that once you have the thiol included inside your resin, the rates go up a lot faster and sooner, which is exactly what we want to see. And this is also reflected in the print scope with these thiol doped resins. As you can see right here, here's an example of that same resolution print with the thiol inside. I'll get some pretty good detail, even at say 6 seconds or so. And if we take a closer look at 12 seconds, we can see these little nice little squared rectangular pixel arrays in the middle. And we can zoom in a little further to see basically these resolutions down at the microstructure scale. We can also, again, use these resins to print out more complex objects, like this 120 phase cell here. And we can see that the digital rendering and the actual print look very close, lots and lots of nice detail. We can then zoom in a little bit further. So let's say instead here, we go to the millimeter and then to the micrometer scale. And we can see those little like stacked layers right there are very, very sharply defined. They look very, very clear. You can see them very clearly. And that is exactly what we want to see when it comes to printing out objects with these resins. So essentially, we have shown that we have demonstrated fast and high resolution 3D printing with visible light. So where do we go from here? Where can we take our research further? The first, again, as noted before, is the biocompatibility. As noted before, visible light is less energetic, and this allows for biological applications such as printing out organisms, such as, for example, coral scaffolding with the coral polyps themselves for use in like revitalizing depleted coral reef ecosystems. Another opportunity, of course, is that you can print out tissue mimetics with these for like human tissue. And that enables more accurate modeling for like making new drugs and treatments for different diseases. Other application for this course, this is going to be a little more theoretical, is just something to quantify and improve our resin efficiency with the different catalysts that we use, possibly synthesizing some new ones. What that enables us to do essentially is to see like which wavelength of light and the corresponding intensity of that light allows for the most efficient 3D printing that's the most environmentally friendly. And that's basically my current project that I'm working on to optimize our 3D printing and take it to the next level. With that in mind, I'd like to give some acknowledgements. First of all, to my Professor PI, Professor Zach Page, who's in the audience right here. Thank you so much. And my mentor for these product research, postdoctoral scholar Dewan, who is now a scientist in South Korea. We wish him the best of luck in his endeavors. And another crucial collaborator, our third-year graduate student, Lynn, right here. Thank you all so much. Without them, there would be no research. There would be no 3D printing advances that you see here. I cannot thank them enough. And finally, I would like to thank all of you for coming to my talk, and I'll happily take any questions.
I only have time for one or two short questions if anybody has one.
How much improvements do you have? Well, you mentioned that you have like 4 types of resins that you start doing the test. So which were the results about comparing each of the 4 resins that you tried to test? Which were the fastest?
Which was the fastest?
Yeah.
Generally, for the most part, the 405 nanometer BAPO was usually going to be the fastest one, just simply because you're having that violet light, which is more energetic. However, though, all of them have pretty appreciable increases in speed compared to like previous visible light printing methods, which can take like minutes, several minutes to make just one layer. Whereas in here, you can basically get a layer in like seconds, as we see with the resolution prints. Did that answer your question?
Yeah, probably I will come to you and you could talk more about that.
We'd be happy to take it. Anybody else?
All right, thanks, Kevin. You give me that lapel mic now. All right, thanks, Kevin. Kevin comes from Dr. Page's group, and most of the CAMD faculty are in the mechanical engineering department, but Dr. Page is holding down fort in the chemistry department for us, so we're glad to have him. All right, so our next presenter is Lakshmi Pudel. I apologize if I'm not pronouncing that correctly, and they'll actually be joining us virtually, so let me stop the share and allow you to share your screen, Lakshmi. And
okay.
All right, you should be able to share now.
All right. Let's see. Okay. Can
All
everybody
right,
see
great.
the
We can see it
screen?
on our end.
Great. Hello, everybody. My name is Lakshmi. I'm a research fellow at the University of Michigan. So the talk I'll be giving about is the work that I did during my PhD dissertation research under the guidance of Dr. Zhang Shah. So basically, as we know, customer demand is changing. Can I move this screen out of the way real quick? So customer demand is changing where, they're requiring more and more customized and personalized products. Manufacturing is trying to catch up, but still based to this traditional line-based manufacturing where things are basically set up in line in sequences. With standard processes that has mass manufacturing thrive. But this approach of manufacturing is rarely able to match the changing demand of customized product. That is where this concept of swarm manufacturing comes into consideration. It's basically a novel paradigm for distributed manufacturing where networks of micro factories are established at different geographic locations to enable on-demand manufacturing. It does so by enabling a group of heterogeneous robots that work together to manufacture a variety of different products at each of these micro factories. And as it can be seen that it has several benefits, both in terms of economic as well as societal aspects. So in terms of economic dimension, we can see the current state of supply chain has been really disrupted with a lot of different factors. And if we had this, individual microfactories at certain geographic locations, people that need any kind of product can be manufactured locally with using different local dimension, which significantly reduces this complicated supply chain that are very fragile at this point. And on the other side, it also has a lot of societal benefits because it promotes use of local products for manufacturing, as well as promote entrepreneurship and so on. So corporate 3D printing is a primitive form of swarm manufacturing, where basically all these cooperating robots are mobile in nature and do primarily 3D printing. Such cooperation is achieved by using the concept of this new concept called chunk-based printing, where we divide an entire part into multiple smaller chunks, as we call it, or smaller pieces, if you will, using a chunking strategy so that the chunks can be assigned to individual robots, which can then work in parallel to print the assigned chunks. Since prior to this one, there was no existing approach that allowed us to take a big, big part and just take a model of that object and assign to multiple robots for 3D printing. So we discretize this entire process of 3D printing using multiple robots into multiple stages. The first step is basically, taking this part and discretizing into smaller chunks. And so in this case, we use some sort of chunking strategy to divide the part. Once the part is divided into smaller chunks, we then create a print schedule, which basically includes chunk assignment as well as sequence generation, which can be represented using this directed concept of directed dependency tree, where each of these nodes represent a chunk, and the edge connecting two nodes basically represents the dependency relationship going from chunk to chunks, basically. And once the schedule is generated, we do path planning and motion planning and basically implement the print schedule to print the part. So the first step of this corporate 3D printing is chunking, which is, like I said, a process of dividing a given geometry into smaller chunks so that they can be assigned to individual robots. However, it's somewhat different to the conventional geometric partitioning problem, as it requires some additional consideration. For example, chunking should allow simultaneous multi-robot printing, right? That's how we reduce it whole time. And the bonding between the chunks should also be formed while the printing is taking place as well. We cannot wait until all the chunks are printed and then have somebody else come and glue the part together. So to achieve this objective, we introduced a concept called slope surface chunking strategy, where planes at an angle are used to partition a part into multiple chunks, as shown in the figure here. The chunking is done along one axis first, in this case x-axis, and then along another axis, resulting in multiple number of chunks. So in this case, there are 30 chunks in total. And the figure at the bottom shows how the addition between the chunks takes place as the heated nozzle comes in contact with already printed chunk here, right here, and it deposits new material. The heated nozzle, softens the previous material, and the contact between the two material takes place, and the addition is created right there. We've studied some mechanical properties of this chunk-based part. I'll be happy to refer any of the previous studies that we've done, but these are not highlighted in this presentation. So the second aspect of the corporate 3D printing is scheduling, which includes chunk assignment to the robots, printing robots, and generating print sequence to undertake such printing. So if you look at this, same rectangular board that I showed previously, and once a part is chunked, we can represent the print schedule using a directed dependency tree. In such representation, all the chunks in the same row gets printed together as shown in here, and all the chunks in the same column, so there are 4 columns in total. Each of these individual chunks, each of these individual column of chunks are printed by one robot. So for example, a single robot prints all these chunks, this one, second one prints this one, and so on. So in addition to this, we also, while generating such print sequence and assignment, we need to ensure that we avoid any kind of conflict. Right? This conflict could arise due to some sort of chunking strategy, or it could also arise due to robots are printing different parts, and want to make sure that when they travel from one location to another location, they do not collide with any other printed part. And we also want to make sure that during any print cycle, they do not collide with one another either. So this type of scenarios are to be avoided while generating a print schedule. And finally, another aspect of scheduling would be to, once you have a schedule, we're going to find out how long it takes to print the entire part, right? So we want to make sure we utilize the directed dependency tree that we use to represent the print schedule. So we formulated a mathematical formulation to kind of evaluate the print schedule to see how long each print or total print takes. I've not put that equation in here because it's just this is short talk, but if anybody is interested, I'd be happy to send the reference material later on. So combining these two, so combining these two frameworks, the software components or frameworks that I talked about previously with the chunking, scheduling, simulator, just to kind of demonstrate, kind of simulate how printing takes place, and some of the hardware development done by Ambots, a startup based in Fayetteville, Arkansas, we're able to actually demonstrate the actual printing of a really large object using these 2 printers. As you can see, these 2 robots are printing basically chunks that have been pre-assigned to them. And as they need to move from one print location to another location, a mobile platform comes and picks the printer up, moves into a different location. The printer starts printing the assigned chunks again, and the process continues until the entire part is complete. So in this case, the part that was printed was about 1,000 millimeter by 350 millimeters, so it's pretty large. So as you can see, how this concept of chunk-based cooperative 3D printing can be utilized to print something really large scale. And then finally, I want to highlight some of the future direction that we could, or even the other researchers could take to further the concept of cooperative 3D printing. So we believe that this is just the inception of, we're just at the beginning of cooperative 3D printing, multi-robot printing, whatever you want to call it. And there are a lot of work to be done. And some of this, it will probably take a group effort of the whole community to further this research. Some of the potential avenues could include, in terms of chunking, this could be developing new chunking methods, or even doing a further study of mechanical properties of chunk-based part to kind of basically reinforce some of the studies that we've done. In terms of scheduling, and some of the new developments could include generation of print schedules that are more agnostic to the chunking strategies, and even leverage some of the existing studies in multi-robot field to come up with new printing strategies. Aside from this chunking and scheduling, some of the other research avenues could include using layer-based printing, which is basically if you even go for discretize the entire part further down into layer-based and assign individual layers to printing robots and have them collaborate while they're printing individual layer, that could provide more control to the user. At the same time, we can even go further down to a G-code level compared to a layer level and assign each of these lines to robots and have them collaborate while they print this individual G-code line. This would provide more flexibility to the user, but at the same time, it probably require more rigorous research work in future. With that being said, that is all I have. I'll be happy to take any questions.
All right, thank you, Lakshmi. Are there any questions? I can relay them if we have any. All right, I don't know if there's any questions out here, so thank you very much for being able to join us virtually, and we'll go ahead and move on to our next speaker.
Let's share this.
All right, so our next speaker is Aidan Moyers. So Aidan, come on up. Load up your presentation. Do this again every single time. You remember to share my screen. There we go. All right, I'll turn it over to Aidan. There you go.
And then there's a pointer.
Am I audible? I believe so. All right, well, my name is Aidan Moyers, and today I'll be presenting the work of the COVAR group on microscale, micro cold spray of patterned thick films and microscale devices. We have a lot of students in this group. That would be me, Stephen Beershank, Aditya Goyals, Scott Burleson, Derek Davies, and Jeremiah McAllister, many of which are in the audience. And our for faculty, we have Michael Gamage, John Keto, Michael Becker, and Dr. Kovar. So for this presentation, we'll start with the overview of what our objectives for this process are, what its capabilities are, how the process actually works, the frontiers we're trying to research currently, and the conclusions we can draw from it. So the objectives are that we want to additively manufacture thick film devices, which are roughly 2.5 dimensions, so it's an X and a Y, and then a Z that has micro scale thickness. So we want to be able to directly write metals and other ceramics at room temperature and without post-processing. This will let us be compatible with many kinds of ceramics and other substrates because we don't have high process temperatures. We want to be able to tune properties of the final film and the microscale device by turning processing knobs. So the capabilities of our process, the top row is all silver onto various materials. So on the left, it's a small RF antenna of silver written onto a hard ceramic. And in the middle, on the top, we see an SEM line of silver onto a stub. And this shows the typical cross-section of a film, which is going to be roughly Gaussian distribution that you can raster along an axis to produce a film and along 2 axes to produce a thick film. So we can actually do really fine feature resolutions using masks. So the image on the far right is a silver written through a mask. And then after we remove the mask, we can have microscale features. So in the bottom, we have ceramics deposit onto things. So it is an alumina line in the bottom left, written across ABS plastic, stainless steel, and alumina with one set of conditions. So this shows we have a pretty versatile process that can deposit ceramics onto a wide variety of substrates. In the middle, we see silicon carbide deposited onto a washer. So this is silicon carbide, a very hard ceramic used for abrasives and various coatings, deposited onto a soft galvanized coating. So you can imagine there's a lot of process disparity there for what kind of properties you can get. And on the right, you see lithium niobate, a technical ceramic with some interesting electrical and optical properties written onto silicon. So there's a lot of capabilities that we can do. The actual process starts with taking a micro or nano powder, aerosolizing it, breaking up any agglomerates, going from snowflakes to snowballs to hopefully individual grains of water ice. Then we accelerate the particles through an aerosol nozzle, and we impact them into a substrate at high velocity. So from the left 2 items here are engineering considerations. The right 2 items are currently mostly simulations and the areas of our active research. So one of the items is to actually figure out what the particles do in the nozzle to predict the particle velocity to perform aerodynamic simulations by taking our whole system and then simulating its geometry and how the air flows through it with varying considerations. And this allows us to put a particle inside of the gas stream and then figure out where it hits the substrate and at what velocity. And we have found that generally velocity is one of the most important impact characteristics to predicting what actually happens in our process. When it comes to actually figuring out what happens in impact, the particle impacts happen on such small length scales, nanometers or micrometers, at kilometers per second perhaps. And so these strain rates are too high to actually capture on a camera. So there's no high speed that can really allow you to get that resolution in both space and time. So what we do is we actually simulate them atom by atom in a scale model through a process called molecular dynamics. And so here are 2 results. One of these on the left is a silicon carbide particle hitting a silicon carbide substrate. And we can see is that it's impacting at an angle, and the angle actually prevents it from adhering well. And so on the right, in contrast, we see yttria impacting yttria at a much lower velocity, but it does adhere. And so what we use molecular dynamics for is predicting what kind of regime we actually see adhesion and the deformation behaviors that we want to use to get our final film properties. And so the final frontier of our process is working on physical experiments, studying the process property relationships. And so this is going into one of the other really big areas of our field beyond just the velocity of impact, but the actual particles that we're depositing. So from the x-axis on all three of these plots is the same. It is the temperature at which we pre-treat our nanopowder. And so this little image right here shows a very loose snowflake agglomerate. And as we increase the heat treatment temperature, the size of the agglomerate drops as it densifies first, and then it actually increases again as multiple agglomerates come together. And so the result is that we're going from snowflakes to snowballs, and then maybe even just ice. And so what this actually does is it changes how our powders actually behave in the gas. So it changes what speed they're impacting the substrate, and also changes how they impact the substrate. So we can see in this middle plot, as the treatment temperature goes up, which changes the agglomerate morphologies, we actually increase the relative density. So as the heat treatment of the pre-processing changes, we actually get a different relative density of our final result. So we can actually tune between porous films and dense ones. And this has a final impact on our desired property. In this case, this was a silver film. So starting with silver nanoparticles and densifying them into larger agglomerates, what we actually see is that the original denser films with higher pre-treatment temperatures result in a more dense film, and in turn, a higher conductivity film. The conclusions we can come to are that micro cold spray can be used to produce patterned ceramic and metal films at room temperature. And these work at a variety of input processes and output substrates, so it's quite versatile. The film microstructure is a function of particle size and of impact velocity, and our current work focuses on depositing multiple materials to create microscale devices. So we have a lot of acknowledgements and sponsors in our group. Does anyone have any questions?
What method are you using to accelerate the particles?
Oh, I forgot to go over that. So we I don't think it's going to go back to this point. So we start with the particles and we aerosolize them with some kind of powder bed, and we flow gas through it to aerosolize the particles. And then this aerosol passes through a nozzle from a high pressure side to a low pressure side and accelerates it to about the sonic velocity of the gas. In our process, we accelerate it from about atmospheric pressure upstream to a vacuum chamber downstream. Any other questions? Yes.
So if you increase the bed temperature, would that help with the adhesion of the particles?
It does for some materials. So the processes that we're actually using, there's a lot of heat generated by the impact itself. So the process temperature within the particles can get up to about 1100 Celsius. So heating the bed a few hundred Celsius can change this some, but not necessarily that much. And there's a lot of applications where you might not want to heat the bed. If you're trying to make a thermal protective coating, you're trying not to heat the substrate and apply a dense film onto it as a thermal barrier. So it is an option in our process, but we often try to avoid it.
All right, thank you, Aiden. All right, moving right along. Our next presenter is Qingang Li. Forgive me if I pronounce that incorrectly. Another member of Dr. Shah's group. And let me pull up your presentation right now. This time I'll remember to share my screen first. Well, I need to stop sharing things. Make sure that we're sharing the right screen. All right, I think you have the floor. Thank you.
Can you hear me okay? Okay, hello everyone. My name is Qingang Li, and I'm a PhD student from Dr. Shah's group. And my research interest is focused on AI-assisted design method. So I'm trying to use some deep learning method and like generative design method to try to quickly connect the designer's design idea to the manufacturing. So today my topic is related to one of our recent research, and it is from 2D sketching to 3D printing. deep learning approach for 3D mesh generation with 2D sketches. So today my topic might kind of shift your focus from the manufacturing to the design part. Yeah. So our research started from the observation of a typical engineering design process, and which could be very iterative, especially in the very early. Sorry, maybe I need to. Yeah, sorry about that. So especially in the early design stage, the engineering design process could be very iterative. And in many cases, 2D sketching is used in the conceptual design phase to brainstorm design ideas and generate new design concepts. So later on, the 3D models will be created for like rapid prototyping and engineering analysis. However, the 3D modeling is very time consuming. Here, I use a blue area and black points to represent the design space and the design concepts. You know, under very limited development time, only a few design concepts can be created, and only a portion of them can be further 3D modeled, prototyped, and tested. So our research question is that, can we automate the 3D modeling process to expedite the design process? And can we generate more design concepts to facilitate the design space exploration? So our research objective is to build a deep learning approach, which could be both predictive and generative to support quicker and more thorough design space exploration to support the design decision of designers. So the predictive function could allow the prediction of a 3D shape from a simple 2D sketch, and the generative function can generate a lot of novel 3D shapes. And also the resulting 3D shape should also be 3D printable, so that user can quickly try their new designs. And here we select the mesh as the 3D representation because it can be directly 3D printable, and also it has good surface quality. So instead of using point clouds and voxels. So this is an overview of our method. And to tackle the challenge of predict 3D shape from a 2D sketch, we introduced an intermediate primitive 3D shape as shown in this red rectangle. And actually, we by using this way, we transfer the 2D to 3D prediction to a 3D to 3D prediction problem. And also considering integrating the generative function into this method, we propose target embedding variational autoencoder method, and we call it TEVE for short. And following the structure of this TEVE, we built a E2D network, which has two encoders, encoder 1 and encoder 2, and one decoder here. So we use the case study of the carbonic design to demonstrate our method. And we need to train this neural network, we need to prepare training data of source shapes and target shapes. So here's the process that we use to prepare our training data pairs. As you can see, starting from the red star, which is the original authentic model, and we first extract its contour here, and then we extrude the contour to the 3D extruded shape. Then the original 3D shape and the extruded 3D shape form one data pair, and we call them target shape and source shape respectively. And this process is done for all 3D shapes that we got in the open source data set. And during training, we divide them to training set and testing set. So here are some results. When the E2D network is trained, we connect the encoder 2 and the decoder to form the prediction network. So here are some results from this network. As you can see here, we can predict an authentic 3D shape from a simple 2D contour sketch. And the resulting 3D shapes can be directly prototyped using a 3D printer. Similarly, we can connect the encoder 1 and the decoder 2 to form a generative network. And given any two different shapes, as the starting shape and the ending shape here, we can get there in transition shapes, in between transition shapes using shape interpolation, and we can also randomly generate lots of novel shapes using random generation. Let's come back to the figure that I showed previously. To answer the first question, we replaced the time-consuming 3D modeling process to a 2D to 3D predictive function, so that the design concepts can be more quickly 3D modeled, prototype, and tested. And also, we use the generative function to create more design concepts for the designer, so the design space can be better explored. So, which answer the second question. So, in conclusion, we propose a method that could be both predictive and generative, and which can connect can quickly connect the idea generation to the prototyping and testing, and which can also allow more thorough design space exploration. We still have some limitations in the current method, because the current method can only deal with the top genus 0 topology shapes, and in the future we try to include like topology optimization with deep generative models to generate more complex shapes. And also we observe that the current generative design method, they generate some structure that kind of organic. On one hand, this is good because people can, or designers cannot think of any of those structures. But on the other hand, those structures are usually counterintuitive to human aesthetic or physiology side. So we try to solve those aspects in our future work. And also for the current work, because the generative solution might not be exactly the same as designers imagine in their minds. So we would like to develop a user interface to allow the input of 2D sketches and the modification of the generative solutions. Yeah, we would like to thank the financial support from NLS, and also thank you all for attending this symposium. Yeah, thank you. Questions?
All right, go ahead and keep moving. Thank you very much.
Thank you.
All right, our next presenter is Doug Sassman. So Doug, if you can come on up, get your presentation loaded, and we'll keep moving. All right, Doug, the floor is yours.
Thank you. Can everybody hear me? Is the mic working? Cool. Alrighty, so I'm going to give a quick overview today. Oh, I forgot to introduce myself. My name is Doug Sassman. I'm in Dr. Kovar and Dr. Beeman's group. This is actually my last semester. I should be finishing up next week, hopefully. So I'm going to give a quick overview, a brief overview on our work on laser sintering of ceramics. So the punchline basically to my talk is that laser sintering of ceramics is really difficult, and it doesn't play well because the ceramics are brittle and sensitive to thermal shock. So you kind of need to engineer some ways around that. And we have two ways that we work on primarily. The first one is indirect selective laser sintering, where we add a sacrificial binder so that when we melt it, when we scan it with the laser, only the sacrificial binder melts and kind of forms bridges between the ceramic particles. But this method does require some post-processing, but we do have the ability to tune the porosity, and I'll talk a little bit about that next. The second method to overcome the difficulties with ceramics is by reducing the kinematics of sintering, the kinetics of sintering. And the way we do that is by a process called selective laser flash sintering, which is very similar to SLS, except that we add an electric field across the powder bed. This method doesn't require any binder or post-processing, and it is targeted towards high density defect-free parts. So I'll start with indirect selective laser sintering. And I'm just going to give a highlight of a new capability in our lab, which is an in situ microscope for the SLS process. So we went into this work with ceramics, thinking that the mixed powder, again, it's mixed ceramic and polymer, that powder behaved very similarly to nylon during the laser sintering process. So we designed this instrument and we actually proved ourselves wrong. So the video in the top is scanning the mixed powder, nylon and alumina, at about 1,000 millimeters a second. And the white circle, which is kind of faint on the screen, represents where the laser is at all times. The bottom video is just plain nylon. So you can see in the top video, not much is actually happening. In the bottom video, after the laser passes, the particles become translucent, which is indicative of melting, and then they start to coalesce. So this led us to a new understanding that the powders behave differently during laser sintering. We actually developed a model to describe that. So just real quick, in terms of the capabilities of the device, it can span the time and length scales of the SLS process, so for example, you need to capture the particle scale dynamics, which are very fast, very small. You also need to capture the powder bed dynamics, which are a little bit larger and a little bit slower. So this instrument, you can adjust those two parameters. It can also operate under realistic manufacturing conditions. So it can operate in a heated chamber. You can image multiple layers because it clears the powder deposition system. And all of the adjustments are external, so the machine can stay sealed the entire time. As I mentioned, with the indirect SLS process, we're sort of able to tune the porosity. And porosity can be beneficial for some applications, especially on the surface. And an example application would be like catalysis, where you want the surface of the solid to interact with some liquid or gas. So in the indirect SLS process, we're able to tune that small scale porosity on the surface, which I'm showing with the X-ray computed tomography images. You can see there's some porosity down at the particle scale on the order of microns. And then with this indirect SLS process, we can build pretty complex 3D parts. And I'm showing the CAD file corresponding to the parts that I'm showing there. Those are green parts, so they still have polymer in them, but we have successfully burned out the polymer and densified the ceramic with that shape. So the second method that I've mentioned to get over the limitations with ceramics is by this process we call selective laser flash sintering. And mechanically, this process behaves or is very similar to the SLS process. So all the mechanical components are the same, except for the fact that we add an electric field across the powder bed. So you can see that there's a power supply attached to a positive electrode, and then we measure the current at the negative electrode. I'll give a more detailed view here. So the image on the top is a top-down view of the powder bed. The gray regions are the electrodes, the white region is the loose powder, and the laser is indicated by the orange arrow. So the laser starts scanning in the positive electrode, and you can see from I'll explain this actually. The plot below is the current through the part or powder bed as a function of time. So you can see as the laser starts scanning on the positive electrode, there's no current flowing, and it continues on into the powder bed. There's still no current flowing until just before it reaches the negative electrode. And then you see this sharp spike in current. And this is kind of the hallmark of successful laser flash sintering. Basically what's happening is the laser is kind of heating the ceramic powder, increasing the electrical conductivity, and then you get current flowing. This is analogous or an adaptation to the flash sintering process in traditional ceramics. So this slide just highlights the capabilities of this process. We are able to produce multi-layer parts. This one is a 35-layer part. And we can also, we can make pretty dense parts. I think these are on the order of 90% local density, but there's still some challenges to work out. The bottom SEM images shows that there's some cracking still, which we're working on now. And that's it. Thank you guys. If you have any questions, I'll have a poster on the indirect selective laser sintering stuff later. And I think Dr. Kovar will be around to answer any questions about the flash sintering process. Thank you.
All right, thanks, Doug. Our next presenter is Nick Rodriguez. So Nick, if you can come on down, we'll get your presentation loaded up. All right, take it away.
All right, hi, I'm Nick Rodriguez. I'm in Dr. C. Prasad and Dr. Crawford's research group. And with funding from Lawrence Livermore National Laboratory, we are developing a large volume, high viscosity stereolithography printer. So we're building this printer intending to print with high viscosity or paste-like resins with the material properties that you can see on left. Notably, we want to print with highly elastic, strong parts that have high temperatures they can operate at. And we intend to build complex geometries with a footprint of 400 by 400 millimeters squared. And this is building off of prior work that we did at Lawrence Livermore, printing UV curable silicones, which you can see at right. So our material choice stems from the tendency for traditional radical initiated polymers to be stiff and brittle when cured. More recently, there's been work into SLA printing with elastomers such as polyurethanes, which do have the material properties that we desire, but silicones tend to operate at higher temperatures and also have better understood aging behavior, which has led to their widespread adoption in industrial uses. We have previously investigated UV curable silicones with a thiolene radical-based curing system, but we observed pretty poor high temperature aging with this chemistry. So we are instead looking into adapting the traditional method of curing silicones, namely a platinum catalyzed hydrosylation reaction, adapting that to be UV curable. There has been some work in using UV to cure these types of systems, but it's been using relatively low intensities with curing times on the order of minutes, preventing its use in AM. So for the large areas that we're hoping to cure with, the high intensities that would be required for short layer times prohibits the use of laser-based or other DLP techniques that are used or available in stereolithography. And we need to develop a new method of patterning light over a large scale. So our solution is using a UV backlit LCD monitor with the film polarizers replaced with wire grid polarizers. You can see a schematic on the right of how an LCD functions with two orthogonally oriented polarizers that each only transmit one polarization of light, sandwiching a layer of liquid crystal. Any pixel of the liquid crystal that's energized will rotate the polarization of light, allowing that light to transmit through the second polarizer. There are multiple SLA printers on the market that use LCD screens to pattern UV or near UV light. However, these printers are highly limited in the types of resins that they're able to print with due to the low transmittance through LCD screens, even monochrome LCD screens. You can see some transmittance data for film and wire grid polarizers in the bottom left-hand corner. And you can see that wire grid polarizers transmit light at every wavelength in the UV and near UV region much more efficiently than film polarizers, even down to 365 nanometers. In addition, since wire grid polarizers are reflective polarizers rather than absorptive polarizers, they don't heat up as rapidly under illumination, allowing you to illuminate the LCD at much higher intensities without overheating the screen. So these features were cured with an LCD that had the film polarizer proximal to the light source replaced with a wire grid polarizer. This LCD had 75 micron pixels, and we were curing a PR48, a relatively easy to cure acrylate resin. And we were curing lines ranging from 2 to 10 pixels and holes 5 to 20 pixels. The smallest lines and holes we were able to resolve were 300 and 680 microns respectively. And these features were overcured from what we intended, although we were able to get features that more matched the intended features when we cured with lower intensities. We just failed to resolve the 2 pixel line at these lower intensities. So on the right, you can see the whole printer assembly, where the light patterning components that I just discussed would be illuminating in an upwards direction from below the release film. That's not pictured in this image, but it is there. This type of printing, since we are intending to cure paste-like resins, we can't use a resin bath like is typical in SLA systems, because the stiffness of the uncured resin often exceeds the stiffness of a cured elastomeric structure. So rather, we are coating 500 micron layers of resin on the release film, each layer, using a slot die coater and a progressive cavity pump. And you can see on the left, the entire printer is enclosed in a UV-proof enclosure. So the release film onto which the resin is coated is wound between two rollers that can control the tension in the film. To coat each layer of resin, the film translates to the left while the slot die coater is extruding a line of paste, spreading it into a film of about 500 microns. After the curing step, which again is illuminating from below that film, the rollers detension the release film, allowing the part to be raised up without exerting any force onto the cured layer. At the desired layer height, the rollers will retension and initiate separation. And by peeling off the release film from our cured structure at these high peel angles, we're able to decrease the separation force by over a magnitude compared to if we just tried to lift the part straight off of tension Teflon. You can see our 385 nanometer LED array at left emits a light field of 2000 milliwatts per centimeter squared over an area of 400 by 400 millimeters. And at right, our slot die coater there is recoating a resin it can recoat viscosities exceeding 200 Pascal seconds or 200,000 centipoise in about 500 micron layers. And this was our first full-scale 2D patterning of a resin. This is another acrylate radical-based resin, and the pattern is about a foot per dimension with features as small as a few millimeters. So in addition to curing acrylate resins, we have also had some success curing the platinum catalyzed silicones that I discussed as the motivation for our work. That's seen at the top right, and the UT and Livermore logos were cured with an intensity of about 80 milliwatts per centimeter squared for 20 seconds, which is about 2 orders of magnitude higher flux than commercial resins typically need to cure. So curing these parts would raise the temperature of the LCD screen even after we replace the film polarizers with wire grid polarizers. It still raised the temperature of the screen to about 80 degrees Celsius. And so we've developed a COMSOL simulation to model that temperature, and we're exploring techniques to reduce the temperature of the LCD during printing. With a UV curable silicone, we hope to explore applications like inflatable structures and soft robotics that you see in the top left, as well as printing graded density lattices to have a pressure distributing prosthetic socket liner that you can see in the bottom left. Finally, we hope to develop a series of design guidelines to investigate the resin deflection during printing based on the resin stiffness. And so finally, I would like to again thank Lawrence Livermore National Laboratory for funding this work, and I look forward to answering any questions now or during the poster session.
Thank you very much, Nick. All right, our next presenter is Oliver Weeks. So Oliver, if you want to come down while I get your presentation loaded, we can keep these lightning talks going. All right, Oliver, there you go.
Thank you very much. We have the
your options like?
Where's the quick? Oh, there it is. Okay. Yes. Hello, everybody. Can you hear me well? Perfect. All right. My name is Oliver Waits. I am a part of Dr. C. Prasad and Dr. Tahrani's group. And today I'm going to be sharing with you research into reactive extrusion additive manufacturing, known by the acronym REAM, specifically with applications to magnetically actuated shape memory thermoset composites. So REAM is an additive process that makes use of a two-part thermoset resin. So you have your catalyst reservoir and your resin over here. They are metered at the appropriate volume ratio and then pumped through a static mixing nozzle, which induces turbulence in the flow, mixing your resin and your catalyst together. The material is then deposited and allowed to cure in situ. So there are a couple benefits associated with this in situ curing. First, you mitigate anisotropy by promoting cross-linking between part layers. Additionally, there's no need for external heating elements, right? Because this isn't a melt extrusion process. It's not a sintering process. The only energy associated with running the system is the energy used to position your nozzle and to pump your materials. By using a two-part thermoset formulation, you sort of open the range of material properties that you can get from REAM parts by virtue of just having a wide variety of compatible material feedstocks. Additionally, if you include multiple pumps, multiple nozzles, you can achieve multi-material mixing and extrusion. Using a liquid feedstock promotes the very rapid building of parts because, again, there's no melting, there's no laser sintering. You don't need to process your materials during printing. You simply mix and extrude. Additionally, a liquid feedstock is going to be more receptive to inclusion of solid additives because, again, there is no need to melt the material. It is already in liquid form. You add your solid additives, degas the material, and it's ready to be used. So we've got 3 REAM systems. I'll be sharing 2 of them with you today. This is our first generation desktop system. So you can see we've got our material reservoirs. Our metering system in this case is a piston pump with a fixed volume ratio 4:1. And what we've done is we've taken an existing off-the-shelf FFF printer and converted it into our REAM system by replacing the original FFF printhead with our mix manifold and mixing nozzle. We've also converted the metering system actuation from pneumatic over to stepper actuation. And so this allows us to control the pumping system with the 3D printer's motherboard such that we get appropriate material deposition. We also have a robotic system that makes use of a 6 degree of freedom robotic arm. Specifically, we're using a Yaskawa MH80. And we're also not using piston pumps, right? We're using these progressive cavity pumps that move discrete pockets of your feedstock material through the length and out the outlet. And by using these progressive cavity pumps, we can use materials with volumetric ratios that aren't necessarily 4:1, right? Because the desktop system, you have a set ratio. Here it is adjustable. So we've kind of opened the window of compatible materials. Additionally, by using a robotic arm, we're not limited in printing in planes parallel with the ground, right? So we can do conformal printing. Here is the desktop system in action. We're printing a Longhorn, which is approximately 200 millimeters from horn tip to horn tip, layer height of 2.5 millimeters. And you can see we're almost done with the first layer already. This is a very quick process. The material that we're printing with is a densely cross-linked epoxy. Just for your edification there. So a couple
of notes about Ream systems generally and their capabilities. As I mentioned once or twice by now, we can achieve very large build rates in excess of 3 orders of magnitude greater than your standard FFF system. So here we have down at the bottom of this graph here, a Stratasys Mojo, which is a fairly typical entry-level desktop FFF system. And over here we have our desktop Ream system using the volumetric flow rate that you just saw in the previous video, just over 100 milliliters per minute. Though it is notable that we've demonstrated volumetric flow rates of 220 milliliters per minute. We can process highly viscous materials up to 100 Pascal seconds, as well as materials with high volume percentages of solid additives. So be they carbon fiber to increase part strength, or active additives such as iron oxide to impart magnetic properties to your composite materials. There's a low energy input because, again, the only energy associated with using the system is the energy that goes into positioning your nozzle and pumping your material. Nor is there any energy associated with curing your parts, right? This is an in situ curing process. So there's no need to put your part in an oven, for example, after part creation. So I mentioned during the title slide that the motivation, at least for me, with use of Ream is the creation of shape programmable magnetically active thermoset composites. So let me explain what shape memory polymers are really quick. They work as follows. You have your original as manufactured shape created with your shape memory polymer. You heat it above the glass transition temperature, and this allows the constituent polymer chains to move more freely and slide against one another. You deform your part into a desired temporary shape while it is at this elevated temperature. Afterwards, you cool the part, and this locks in the strain energy. So you've got this semi-permanent shape down here. And if you want to return to your as manufactured shape, you simply heat your part once again above the glass transition temperature, and this allows the polymer chains to release that stored strain energy, and the part will unfurl back to your original shape. Magnetic polymer composites, as you may have guessed, are polymer matrices with embedded magnetically active particles. And so you can get a variety of deformation modes from such composites, depending on the orientation of the composite and the orientation of your external magnetic field. So you can get torque, bending, force that will lead to either elongation or compression. And as is the case with any magnetically active material, if it's not rigidly fixed to something and you can manage to overcome friction and or gravity, you can also get translation when exposed to an external magnetic field. So what we've done is we've created a multi-material composite consisting of a shape memory polymer backbone over here, the SMP, with a magnetically active elastomer, an MAE, placed at the edges. So what I've done is I've heated up the SMP with a splash of hot water that you saw at the beginning of this video. I'm shape programming it now. I'm holding deformation. It has since cooled, locking in our temporary shape. Let me move my laser a little bit. There you have it. And then now I will return to the as manufactured shape by again heating up the part with hot water. And as you can see, the return is rather speedy. So, any questions? I have a poster down here to my right. If you'd like to ask anything later, I can share with you aspects of future work, etc.
Thank you. All right, thank you very much, Oliver. All right, our next presenter is Tim Phillips. So Tim can come on down. We'll pull your presentation up. Yes, and we have one more presenter after this. So we're on the home stretch, guys.
All right, thank you, Jared. My name is Tim Phillips. I'm a research fellow here at University of Texas, working under the direction of Joe Beeman. Today, I'm going to be talking about some of the work we've been doing with material and application development for laser powder bed fusion. So the first application I want to talk about is additive manufacturing of lithium-ion batteries. So we've been able to use laser powder bed fusion to additively manufacture high-performance battery anodes and cathodes. Now, in your traditional lithium-ion battery, you have an anode and a cathode, collectively known as your electrodes, and they're quite thin. They're about 100 microns thick, or the thickness of a sheet of paper. So to give them structural integrity, they're mounted on some foils, so an aluminum foil or a copper foil. And to get the final battery cell, you would stack these with a separator between them, and then you wind it, fold it, or stack it to build up the large battery cells that you're familiar with. Now, the challenge is that those current collectors, those foils that we use there, take up a lot of space in that final battery, but they don't add anything to the actual capacity of the battery. So what we've been able to do is remove those current collectors and instead use carbon fibers within our material matrix to build up much thicker electrodes that still have high performance. And when we do this, we're using additive manufacturing to build these, so we can take advantage of the geometric freedom that AM affords us and make conformal battery electrodes. So imagine working on a device, and instead of picking a battery out of a catalog, you can actually design a battery, both the geometry of it and the capacity of it, that meets your specific needs. Another application we're working on is additive manufacturing of pharmaceuticals. So to do this, we take a pharmaceutical drug and mix it with an edible polymer and use laser powder bed fusion to create personalized dosage forms. And when we do this, we're actually creating what's known as an amorphous solid dispersion, or ASD. What that means is that when we process this material with a laser, we melt the polymer, and the crystalline drug actually dissolves into that liquid polymer and gets locked in its amorphous state. And the amorphous state of this drug has orders of magnitude higher water solubility than the normal crystalline state. And so that means it has much more availability within your body, and it's a higher performance drug. So using additive manufacturing here, we're not only able to just create personalized dosage forms that are tailored to individuals, we're also able to create a product that has higher performance than if we took those same base materials and just put them in a pill. Another aspect of what we work on in our lab is developing advanced control methods for laser powder bed fusion. So to do that, we've created a custom open hardware or open platform SLS system. You see that here on the left. And I want to talk about one of the applications we've used this on, which involves our high-speed thermal camera. So during a build, we'll use our high-speed thermal camera to monitor the build conditions. And then we'll later identify correlations between what we can measure with our camera and our final part properties. So in the study in the middle, we're looking at the temperature that we measure with our camera and comparing that on the y-axis with the ultimate flexural strength of some parts that we're building. You see that there's a pretty big range here in the temperatures that we achieve, and that results in a pretty big range in the strength of these parts. And so we've taken that information and built a controller around that that can control our laser power to produce a much narrower range of these temperatures. And that's the blue data shown in the middle graph. And that results in a narrowing of our standard deviation of flexural strength as well. So using this method, we're able to create much more repeatable and much more uniform parts. We've taken that concept and expanded it into metal additive manufacturing as well. So here we're using some physics-based modeling and machine learning to predict optimal processing control parameters, and using those machine learning models to assess performance in situ during our building process. The images here are the results from one of our studies where we were trying to control the melt depth while we're building a certain feature here. On the left side is what we would expect to see if we didn't have this intelligent control process. So the red information, pull up my laser pointer. All right, this red information here is showing the melt that's created by the laser. And the profile of that is seen on the image below. You see it's got a lot of variation here, where the black line on this bottom graph was our target melt depth. So there's a lot of error between what the system's doing and what we wanted it to do. But when we use our physics-informed controller, we get the results on the right. And on the bottom here, that green line is now our melt profile. You see there's really good agreement between that profile and our target melt depth. So again, using this process, we're able to have much more control over the outcome of these parts. So those are just a few of the projects that we're working on in our lab. I have a poster at the back with more details on the additive manufacturing of lithium-ion batteries, and I'm happy to take any questions.
All right, thanks, Tim.
Yeah.
All right, last but certainly not least, we have Aaron and Georgina from Dr. Cullinan's lab who are going to come up and give their talk on microscale selective laser sintering. All right, there you go.
Second. All right, so hi, I'm Aaron, this is Georgina. We're both part of the Nanoscale Design and Manufacturing Lab here at UT. We work with Dr. Michael Cullinan. Today we'll be going a little bit over the microscale selective laser sintering project. So here's an overview of the system. On the right over here, we have a slot die coating system, which lays down a thin layer of nanoparticle ink. Right now we're using copper and silver. That's laid down onto a substrate, which rests on top of this nano positioning stage here in the middle. This helps us this gives us XY control during sintering. That helps us do things like align each layer, as well as expand the range or area in which we can sinter in. So this stage is then shuttled over to the optical subsystem here on the left. And that just consists of a DMD and a set of lenses that focuses a desired pattern down onto the layer of ink that was previously deposited. And so this process is repeated several times until a desired part is created. So some of the applications of this technology, one that we're particularly interested in is the fabrication of interconnect structures in semiconductor packaging. And this is because they're moving towards finer pitch and higher aspect ratio structures. And some other applications that we're looking at include MEMS, microscale medical devices, or lightweight structural elements such as this lattice shown here. So most of our experiments or parts that we've been able to fabricate have been done on glass slides as our substrates. We've also done some parts on silicon wafers with different coatings in the past as well. There are a couple examples of dot arrays here at a couple of different pitches and diameters. We also have this Longhorn, which notably has a feature size or minimum feature size of 10 micron at the tip of the horns. And also here we have the MDML lab logo. And so one of the major challenges to creating these nice looking parts is understanding the how the heat spreads during this process. Currently, one of the challenges is actually we're seeing parts that are outside of the laser exposure that are either partially sintered or fully sintered. And that's just due to the heat transfer from the surrounding. So Georgina will be speaking a little bit more about the simulation side of that to kind of understand this problem. So.
Thank you. Okay, so as Aaron mentioned, one of the major challenges that we face is achieving near net shape parts because of the heat affected zones that form during sintering. And so to try to solve this issue, we're looking at modeling the micro SLS sintering process. So there are two main advantages to modeling the sintering process. The first is what we've discussed, which is in trying to correct for the heat affected zones that form during sintering. So if we can predict how the heat affected zones are going to form, then we can make in situ corrections to the laser heating profile to account for how heat will spread. And this will get us more towards the direction of achieving near net shape parts. The second advantage is that if we're able to predict the physical, electrical, and thermal properties of the manufactured parts prior to printing, then we can specifically optimize and design our sintering process parameters to yield the properties that we'd like to see. And so to achieve these goals, our modeling process is broken up into two main particle scale modeling efforts, which feed into each other. The first is modeling nanoparticle, solid state nanoparticle sintering, and the results of these simulation feed into the second modeling effort, which is modeling the thermal conductivity of the powder bed. So the knowledge that we gain from the thermal conductivity will allow us to calculate new thermal profiles, which are fed back into the solid state sintering models, and it just cycles through. So now I'm going to go into a bit of detail on the modeling efforts. The modeling of the solid state nanoparticle sintering is done using a phase-field modeling approach, which where the sintering is driven by the minimization of the total energy in the system. And this total energy is a function of the bulk free energy, the interface energy, and the grain boundary energy. So this slide shows a video of the simulation applied to a 2x2 micrometer bed. What we can see in this video is that we have initial stages of rapid neck formation between the particles, and then the necks grow and we see densification and shrinkage. So the evolving particle configurations from beds such as these are passed into thermal simulations to calculate the thermal conductivity of the powder bed. The thermal simulations use a 1D approximation of steady state heat flow, where heat flux is applied on one end and the other end is held at a constant temperature. And so to calculate the thermal conductivity, we use the 1D approximation of heat conduction using Fourier's law, but modified to account for the non-uniform surface area across the primary direction of heat flow. And so using the sintering simulation and combining that with this, we're able to get curves that relate the thermal conductivity to the density of the powder bed. And so the end goal with all of this is to use these particle scale thermal and sintering simulations to inform a larger bed scale model, which will be able to make predictions of the temperature in the powder beds, as well as predict the final properties of the sintered parts. So that's it. Thank you for listening. And we will be at the back with posters and also get questions now.
All right. All right, thank you very much to everyone that presented, not only for giving wonderful presentations, but for doing a remarkable job of staying on time. So I definitely appreciate that. So we'll move in now to our poster session. So for those of you that are joining us virtually, we'll give you a little bit of a break, but we ask that you join us back at 4 o'clock Central Time. And we'll have an industry roundtable discussion where we can discuss some of the future directions that we can head for some of our research projects. But for those that are here, we ask that you grab some snacks. We have some drinks and some light snacks. We also have posters. And then like Dr. Prasad mentioned earlier, I can give maybe a couple different groups of tours of the center. So we can maybe split that up into 2 waves. So if you want to come tour the center, you can meet me out here in the front and I'll take you across the street. All right, thank you.